Since this is an ocean atmosphere dynamics course, you expect that sooner or later we're going to start doing F equals ma type of calculations, Newton's second law, and we are going to start doing balances of forces, right? So here we will start with the simplest of all of them, called hydrostatic balance. Static means not moving, right? So if you took a atmospheric column, let's say just like a cylinder, and you have pressure at the bottom, and the force is obviously, pressure is per unit area. Force would be the area multiplied by the pressure in that case. And let's say it has a height of delta z, delta z, and the pressure changes with some gradient, partial p, partial z, partial z. I will keep saying z because this may be watched by people outside India as well. Okay, so you have to live with that. And it has a mass and a density, right? Air has a density, and if you integrate over the volume, you're going to get mass out of it. So the pressure at the top of this cylinder is P plus delta P, the increase or decrease in the pressure over delta Z, and the force by the pressure is delta A. So pressure is acting downward at the top and upward at the bottom. That's how the air column is kept together, right? So that's a simple vertical column of air, and we're going to do force balance on this. So what is the pressure at the bottom? That's P. And what is the pressure at the top? Is P plus delta P. So pressure at the top is given as P at Z plus delta Z, the height that we are climbing up. So it will be simply PZ plus delta P, the increase in the pressure that we are showing here. How do we represent it? Basically, we are looking for delta P, which can be expressed as the gradient of pressure with height dp dz times delta z. Very simple, right? This is the simple partial differential equations you've done somewhere before. So the mass of the air in the cylinder is going to be the cross-sectional area delta A times delta Z, which gives us the volume, times the density, assuming the density is constant. We are not saying, here we are saying rho Z, but we're just going to make it constant and say rho. If it's actually varying with height, you'll obviously have to integrate it from the surface to delta Z. Not a big deal, but you will have to know what the rho Z is, what the function is of density with height. So what are the balances you have to make? Gravitational force, which is pulling the air down. So Fg is going to be minus g times the mass m. So it's going to be minus g times, why minus g? Because z is axis pointing up, and anything that points down is going to be negative in the negative z direction. So minus g times rho times delta A delta Z, just putting the expression back for m. Pressure force acting at the top is also minus P plus delta P times delta A because it's pointing down. And the pressure at the bottom is Fb, P times delta A, pointing up. So if the cylinder is not moving, then all these forces have to balance, right? The upward force and the downward force and the gravitational pull have to be balanced. So delta P plus G rho delta Z ends up being the balance for this system. What does that give us? If you divide by delta Z, you're going to get dp dz plus G rho equals 0. Voila, you've just derived your first equation in ocean atmosphere dynamics. Remember, this can be ocean, this can be the atmosphere. We're just saying air column for simplicity, but if you do it in the ocean, obviously you have to take the atmospheric pressure and then how the pressure increases as you go deeper into the water column. As we had said, with each 10 meters about 1 more atmosphere is added as you go into the ocean. Simple enough, right? So just digest it. I'll come back and we will see what the consequences are of this simple equation, and it is pretty cute. So we will do that in the next podcast. Oops, I didn't want to do that, but nonetheless, let me start this